Again, my name is Raj Manchanda. I'm the Chief Technology Officer at SAMPE, the Society for the Advancement of Material and Process Engineering. One thing I do want to do is in the chat, please, or I guess it's in your Q&A, let us know where you're from. Just as you start to enter this wonderful webinar, let us know where you're from. Just put in a quick note in the Q&A, hello from Poland, hello from Japan, because we've seen the roster. We know that you guys are representing the whole world. So go right ahead and let us know where you're from, and then we will get started. As I mentioned, we have guests from Poland, Germany, Japan, Turkey, England, Canada, New Zealand, Australia. I was talking to my colleague Brianna before. I didn't even know what .pl or .tr meant. So we're really fortunate to have a global audience representing companies such as Dow, Saint-Gobain, Solvay, TaylorMade Golf. Thank you, TaylorMade Golf, for your very expensive and high quality golf clubs. Bombardier, Boeing, Airbus, Lockheed Martin, Gulfstream, Excel, Collins, Huntsman, and our friends from Kohler. So as I said, we really have a very broad group attending today. Keep letting us know in the chat where you're from. I do want to have a special welcome to Dr. Lenitra Tate. She's the one that's really behind this. Dr. Tate and John work very closely together. So she's a SAMPE volunteer leader. We're pleased to have her, and she helped arrange this with John. We also have some other friends on the line, Paul from the APL out of Johns Hopkins, Scott Stevenson, my friend Rick Neff, and my old buddy Bruce Kramer from NSF. So thank you for joining. We're going to start getting going now. I'm going to give a brief introduction for our speaker. John Vickers is a senior leader for advanced and in-space manufacturing capabilities at NASA Marshall Space Flight Center. I'm going to ask John to briefly talk about his career, because he has a storied career. He's received numerous awards from SME. He's a fellow at SME, from AIAA, from NASA. And you know, I want him to talk a little about his career as he started his engineering background from University of Alabama at Huntsville, and what led him to these many career and key leadership positions at NASA. Please, John.
Sure. Well, first, let me say thank you for the invitation, Raj, and to Brianna and Christine. You guys have made this really easy for me to get ready. And then my good friend Lenitra Tate at NASA, she did reach out to me, and so she's the culprit in all this that has asked me. You know, I tell you, you put me on the spot with all these names that you've read off from these attendees. And in fact, I recognize some of them as good friends of mine. So I'll mention a little bit about my career. It did start in about 1980, the early 1980s, 1982. In fact, I went to work for the Thiokol Corporation, and all the different paths that career has taken have been somewhat serendipitous. I'm sort of a person that always says yes to, you know, and I think that's taken me a long way. It's certainly brought me to some really exciting work, both in my career at Thiokol, which was just about 7 years before I went to work for NASA. So I've been in this business for almost 40 years. I did work for a period of time in composites. I still work in that area some from sort of more of a management role that I have today, and I'm a strategic technology planner, and so composites is a big part of the future. When I've stayed in my discipline for my entire career, and that's been materials and processes. And so SAMPE was a big influence on me early in my career, and it has stayed that way continuous throughout my career. So I don't know. It's been a really,
Right.
it's been a career to imagine. I'll just put it that way.
And John, what's amazing is that okay, you went the engineering route, and folks on this call maybe in the STEM fields, and that's great. But look, if we have friends, we have family members, young folks who are thinking about careers, look what you can do. It's amazing how you've applied your engineering degree to where you are now. And I think that's what we wanted to start this conversation by, because SAMPE is a place for that. Many of the other organizations are places that will help you climb in your career. So thank you again, John.
You bet. So I'm ready to get started. With all the press and excitement, we just had the landing on Mars last week, and so I wanted to give just a little brief introduction to that before we start the video. And one of the comments that I'll repeat was from the President of the United States. I was watching live with my wife in our living room as the lander approached Mars. And so they cut to the president, and he was in the Oval Office, wow, also watching live, just like all the rest of us. And then after the landing, he called to congratulate the NASA team. He spoke to my NASA administrator, Steve Jerzik, and he said, "There's nothing we can't do." Right. And so that really resonated with me. But I want to make one more comment, and that was from my wife. So my wife's not an engineer; she's not in this business. Right. And she looked at me and she said, "Who comes up with this stuff?" And so it was just so exciting to see the landing. So I'm going to turn it over.
I was going to say we were having a pre-planning meeting on that, and you tell me, this is an engineering miracle. This is not, or maybe not, miracle is not the right word, but the amount of expense and knowledge involved in making this thing happen, and the potential failures that can happen. So it's really a feat, and you and your team and Lenitra, everyone, we really are grateful for you guys.
Yeah, so I'm not directly involved in this mission, but I love it just like the public does, and you're correct. These kind of missions rewrite the books.
Excellent. I'm going to start.
There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data from the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror, because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
When you look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. Once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
Wow, that was something. So folks, if you hadn't seen it last Thursday, as John mentioned, you got to see it again now, encore presentation. We're so grateful. I'm gonna go over to the next slide, but Brianna, I was gonna ask you, can we run the poll now? If we can run our poll now, the reason I'm asking is because it's really outstanding, the amount of organizations that are represented. So what we want to do as SAMPE, you know, this is all about supply chain. This is all about getting folks together. Can you look at this question, please, and take a quick poll and let us know the type of organization you represent? You know, are you coming from a small, medium, or a large organization, wherever you are in the world? We'd really like to know. So please go ahead and make your entry into that, and we'll just start the presentation right after. Probably give it another few seconds. And I think, you know, again, about this is NASA, Marshall, and any of the folks, Airbus, Boeing, they all need their supply chain to be robust. So I think as SAMPE progresses, we have many offerings out there. We do our annual May event. We have some tooling webinars we do. We have a CAMX expo. We'd love to see you folks out there, but when you touch point with SAMPE, you get to meet our supply chain, and that's what this was about. Go ahead, Brianna. Was there any results on this? Okay, look at that. So we have folks, it's a good spread. It's a good spread, but a lot of large multi-billion-dollar conglomerates on the call. So that's fine. We also, I didn't mention, but we have universities represented, and it's great that Northwestern and NC State and folks in John's area, University of Alabama, Huntsville, they all showed up too, but this is a nice mix here. John, I don't know if you have any remark on that, on the supply chain that you know, we're trying to make robust.
So I do. In fact, I have a couple of slides later where I'll mention that. But I think we, you know, in the government where I work, for sure, we can't do this alone. We have to do that. We have to do this with our partners from other government agencies. You mentioned one of my good friends, Bruce Kramer from NSF, right. And so we work closely with other government agencies that have similar portfolios to what we have in NASA, but with industry and academia, of NASA's budget, far more than 80% goes out the door for support from industry, academia, etc. So
excellent.
So I should have named this slide that we can't get to Mars without composites, probably, because that's what I'm going to talk about a little bit about. And I picked these images just as examples of the composites applications that we use to get to Mars. And I'll start in the upper left-hand quadrant. That's the Atlas rocket that launched Perseverance to Mars last July. So it took 6.5 months to get there. Almost 300 million miles. That's sort of hard to say. And by the way, I was going to mention earlier about how hard it is to get to Mars. Of all the missions to Mars over our lifetime, less than 50% of those
Wow.
missions have been successful. So it's really hard to get to Mars. And you see how that whole scenario about the parachute and the sky crane and the rockets. That's what my wife saw and said, who thinks this stuff up?
Right.
So it was really fascinating. So that's a little bit so on this rocket, you see the large payload fairing at the top of the rocket. That's an all composite structure. I know the solid rocket boosters that are on this rocket have filament wound cases and many more parts of the rocket, and all kinds of other commercial launch vehicles today use composites. Now I'll switch to the upper right hand quadrant, and that shows the aero shell. And so the aero shell is made up of two parts, the heat shield and the back shell, and both of those are primarily composite structures. They protect the rover from the extreme heat. They're about the major diameter of that structure is about 15 feet in diameter. That heat shield has to resist the entry heat in excess of 2,500 degrees Fahrenheit. It's traveling at about 12,000 miles per hour. And it has to decelerate the spacecraft to about less than 900 miles per hour before you saw that parachute deploy. Now, the heat shield is a complex composite ablator that we use. And I didn't check. I think it's the pica material that we use for that ablator. I did check with one of our engineers that's close to that technology afterward, and they have instrumentation, so they get some. You don't get that back, so you don't get to inspect it and see how well it performs. But they have some instrumentation to tell them how well it performs, thermocouples, etc. And my question was, how much recession do you get? How much ablates away? And they didn't think much of that ablated away. So my other point to them was, well, maybe you've got too much margin. And they said they want a lot of margin when they go to Mars.
Right.
for something like that.
John, would you say that the testing, is that pretty much done? Because you mentioned the composites, high performance mechanical properties. Is the testing done at Marshall, or is that done throughout the country?
So this is not a Marshall product. This is a Jet Propulsion Lab product. But they would go wherever there's a lot of testing for that kind of material, and in fact, much of that material development was done at NASA Ames. So all of our centers sort of go where the capability is for those kinds of unique products and testing. So I'll move on to the rover itself, and I really didn't check into the rover about all the composite parts, but you can see some that stand out. You see the legs for the wheels; those are all composite parts, and many more on that rover. Because we're trying, we really want these things to be lightweight. That's the really highest figure of merit for spacecraft is the reduction in mass. But then look at the bottom left quadrant. That's that little 4-pound helicopter. It's the first aerial vehicle ever to fly on another planet. And look at you can see the composite imprint in those helicopter blades. So there's two blades. They rotate opposing each other. They're about 4 feet from tip to tip, and they're just beautiful pieces of composite hardware. I'm gonna go to the next slide. I have a lot of these slides, and it was my intent to just give you guys some highlights. Feel free to ask questions
in the Q&A. Yeah, John, and I want to remind folks, since we do have such a global audience, you are going to, as a benefit of just attending this webinar, I mean, we hope you're all going to join SAMPE, but as a benefit of attending the webinar, you're going to get the slides. So that happens right away. We're not going to send them next year. So tomorrow, you'll see a link with the slides.
All right, great. So this is my and so really, so one thing I want to do up front is sort of apologize as I go through these charts. There's so many contributors to these projects that I really, sometimes I just don't have that awareness. or I don't have time to name all the contributors. So if I don't mention your contribution to some of this technology, put it in the chat for others to see, because you should be really proud of the work that you do. This is sort of my back in time machine chart. And so that image that you see at the top across the center of the page is a filament wound case. And you see a name on it, Morton Thiokol. That comes from the mid 1980s, where we had hoped to go from the steel cases for the space shuttle transportation system to filament wound cases, and that was going to give us a little bit of extra payload capacity. We didn't do that, and we had to find that extra payload capacity a little bit later. But that's one of the projects where, and I don't want to talk. At my age, I certainly don't want to bring up anybody's age in this, but that's one of the projects where Scott Beckwith was a great mentor to a lot of people. And the filament wound case was actually built by Hercules Corporation, where Scott Beckwith was employed at the time. So that's sort of the beginning of my career in composites. And so I just wanted to point that out, the mid 80s. If you look to the lower left, that's the space shuttle display that's on display at the Huntsville Space and Rocket Center in Alabama. And probably nobody knows much, but the boosters that are on that display are leftover filament wound case boosters. They're painted white today. I gave you a picture of when they were first installed before they were painted. So since they're painted white, most people never know that they're actually composite cases. And I helped to refurbish those cases when they came to Huntsville. And in one of those boosters, a lot of us wrote our names. And so I'm not sure which booster it is, but my name's in one of those boosters. And then I just wanted to mention, it's really because of this filament wound case program for the space shuttle program at the time that we invested at NASA Marshall Space Flight Center. And you see two pieces of equipment that we invested in at the time. A tape playing machine. I actually couldn't find a picture of our filament winding equipment. We didn't have digital photographs back in the 80s. And so I was lucky to find this photo. And then a fiber placement machine that we acquired in the early 90s. And so if you want some proof that I actually did some real work some time ago, that you can find a paper online in about 1992 or 93 that I wrote about that fiber placement machine. It's the #1 machine that came out of Cincinnati Millicron.
Oh my
so
God. John,
next chart, I guess.
Yeah, thank you, John. I was just going to point out, thank you for your recognition of Dr. Beckwith. He's on SAMPE staff now as our global technical director, so we're very fortunate to have him. He does have a question. He has, what temperature extremes have to be evaluated on materials prior to using them in the rover?
Wow, in the I would have to look at the temperatures on Mars, but there's very large swings because of the absence of a very much of an atmosphere. It gets really cold, so you have to be able to operate in the very, very cold temperatures, and then during the daytime it gets hot as well. So it's a bit unlike what we would do on Earth, or even unlike what we would do on space, where we can control the temperatures by means. You have to be able to operate in that full range of temperature.
Excellent, excellent. Another question on peak thermoplastics. Did you mention that they are used on the rover, peak thermoplastics?
I didn't mention, since it's not a project that I'm closely involved with, I'm not sure of the types of composites that are used.
Okay, we can look into that, but thank you very much. Let me go ahead and advance the slide for you. Hang on. Okay. There you go.
So it's a really big year for us at NASA. We've just had the landing on Mars of Perseverance rover. This is a few images of the James Webb Space Telescope. It comes out of our Science Mission Directorate, just as the rover does. And I mentioned earlier about rewriting the textbooks. Now, this is a case where we have absolutely rewritten textbooks. I'm sure there's a lot of theses that came out of this work. But it's the backplane for the James Webb Space Telescope. And on the left, you see it folded up in sort of a origami type of method. And that's to be able to get it into the payload fairing. So this telescope is going to fly on the Ariane 5 rocket, and it has about a 5-meter payload fairing. And so the only way to get it into that fairing is to be able to fold it up like this. And so that presents all kinds of complications itself. You see in the little takeaway box down at the bottom how much load this has to carry, because it carries all of the mirrors. You see it unfolded, the two little wings of it unfold, and the mast has to fold up. So you see it completely unfolded in the center image. And that's a lot of actuators that have to work on space. And with all these connections and attachments, it still has to hold this extreme tolerance to the thermal loads. You see it on the right side going into a vacuum chamber. And I think there's 32 of those hexagonal mirrors, and those mirrors are sort of about 3 meters from tip to tip. So it's a huge telescope. It just barely fits into the launch vehicle from a volume perspective, and it barely fits into the launch vehicle from a mass perspective as well. And so this is one of those projects that will have impacts, I think, to the industry from all the lessons that we've learned for many years to come.
John, it's probably a great example of the design team and the manufacturing team collaborating, because, you know, a design engineer, he or she could have this great idea, but then the manufacturers, you know, the way you're talking about the flexibility, that's remarkable. And the scale of it, it's really very pleasing to see that.
Yeah, absolutely. It's really across all the phases of the supply chain. Yep. You have to be able to pick out the correct materials. And so I think this is a very high modulus. I can't remember the material. I knew at one time, and maybe a cyanide ester resin. So it's across the entire supply chain where you have to have that close integration. And
yes.
And I think that this is another one of those, you know, once in a lifetime missions.
Right. I bet you that wasn't the first design that came out. So that's wonderful. John, I'm gonna take it.
Absolutely not. I'm sure there are a lot of subscale demonstrations to get to this point.
Right.
Yeah.
John, I'm going to bring you back 20, 30 years at the start of your career. We have a young person online who's saying, look, I'm a beginner and I want to research and do research in the field of composites. What are the prereqs? You know, what would you say to something like that?
I used to have a boss that was a metallurgist, and he was always after me about how the progress for composites was relatively slow. And I used to say to him, you know, you have a few thousand years of metallurgical experience. We only have 50 or so years of composites experience. In fact, I had made a note. There was Roger Bacon was the person that had found these graphite whiskers that later became carbon fibers in 1958. So that's how far we go back to the very first inception of thinking about using these carbon fibers as a structure. And even in the mid 1980s, he had a quote, and he said, "The full history of carbon fibers has yet to be written. The industry is barely out of its infancy." And I think that's still true. I think that's still true today. We are really still in our infancy. And so what I would say is there's a lot of aspects. My area has been materials and processes, but there's a lot of discipline areas. It depends on your discipline specialty.
Right.
With, like you said, design, manufacturing, all across the life cycle to start. So.
No, thank you. Yeah, John. I think, look, someone like that, SAMPE, I'm going to put on my membership hat now. You got to consider joining. I mean, there's so much great content. There's so much great networking going on. There are chapters throughout the country. I know John's closest chapter might be in the Carolinas. All right, so we're not in Huntsville, but, we do have some activity in Carolinas and throughout the country and the world. So that's an opportunity to join, to meet the folks doing the work. You have folks like Scott Stevenson on the call from Composites world. He's part of the SAMPE world. So these are the kind of folks that you will meet when you become members. John, should I go to the next slide?
Yeah, go ahead, but I'm going to follow up with one comment. I'm just determined at my age that, nobody's going to get too far ahead of me. And so one of the ways I stay abreast of this technology, I read Scott's magazine for one thing. It's a great source of information. I have a subscription and I read that magazine every time it comes out. But you're right. I go to the SAMPE, CAMEX conferences and the other, society conferences where composites papers are being written. That's how you stay abreast. That's the best way. You cannot stay abreast sitting at home or sitting at your desk, I used to say, when we were in the office. So I did want to, so this is a project, so I'm going to shift gears a little bit, that comes out of our Aeronautics Mission Directorate at NASA. And it's been a really successful project. I titled it Remaining Competitive in Aircraft Manufacturing, but really the project was called the Advanced Composites Project. And it was just completed last year after a 5-year research effort and over $170 million. And that was a consortium of government, industry, and academia. And it was, I think it was a 50-50 sort of matching project, although I'm not sure that that's exactly true for all of the members, but there were matching funds. And so what that means, when industry comes to the table and they're willing to put up money, they help drive the areas of research. And so that's really what we want at NASA. We want industry and academia helping us to drive the areas of research. Even though that project is just completed, we're in formulation. This is led out of our NASA Langley Research Center, by the way. And so you see an image of a fiber placement machine they have at NASA Langley. And so they're using that in this area of research. Even though we've completed that project, they're in formulation for another project, and they're calling it HICAM, the High Rate Composites Aircraft Manufacturing Project. And so in formulation in FY21, which is where we are now, hopefully that's a start in FY22. And one of the things they're after is enable something like a 5x increase in production rate. If you see that little, so it just come to mind now. If you see those two images on the right side, on the lower right-hand side of the roller, you'll find an image in that paper that I talked about from 92 or 93 of how the roller from a fiber placement machine works. And that image that was in that paper that I produced back then has been used thousands of times. And in fact, one time I used it, and somebody said, "Hey, that's an image I used in my paper." And I said, "Well, I appreciate that, but you got it from my paper to start with." So,
it's called copyright.
Yeah. So Nick, I try to be really careful about the images that I use in my presentations to make sure that they're either my own, they're NASA's, or that I've gotten permission.
Sure.
So that's a good lesson for somebody that's starting out.
John, on your high rate projects here, can you comment on NASA's utilization of automation? Is this something that's happening really full speed, or do you see it starting to happen? Can you comment on any of that?
Yeah, so I can. I think fiber placement has been, and similar technologies have really been the impetus for increasing the rate. I saw that Greg Haslip spoke at the SAMPE meeting last year, and there was a quote, and I'm just going from memory. He had some quote that high rate production was really the leading factor for composites gaining ground on commercial aircraft. And so you see this image of this fiber placement machine. That's really a latest state-of-the-art fiber placement machine. This one happens to come from the Electro Impact company, but it's that kind of technology. I know commercial aircraft builders. I'll try not to use too many names of companies in this, but the major commercial aircraft company builder in this country is using that same kind of equipment to get these same kinds of rate increases.
Excellent, excellent. Should I go to the next slide?
Yeah, please, next slide. Well, so this is an area, if you heard my title that Raj gave in the opening, Senior Leader for Advanced Manufacturing and In-Space Manufacturing. This is really a new nascent area for us at NASA, but we see a huge payoff. In fact, when I get off of this call, I'm going to be a little late for a call with DARPA, and they have a solicitation out for in-space manufacturing technology. So we see in the industry great benefit from being able to manufacture in space. If you look back to the telescope that I talked about that has to be unfolded, it's at the very limit of its size that we can launch from Earth today. And so the bigger we can make those telescopes, we'd like to make that telescope, twice or 3 or 4 times its size, so that it can see further and further into space with more and more clarity. But we can't do that today. We're at the limit of the size of those because they're constrained by the launch vehicle. So you see this image on the upper left-hand side. That's a demonstration. That's called our OSAM-1 mission. And that, by the way, my good friend Lenitra Tate, that was led out of a program that she used to be the manager for, and she's moved on now. But that's the OSAM-1 mission. And the robotic arm that you see is called the Spider. And what it's doing, it's assembling parts of a communication antenna. So each of those segments or leaflets, if you will, are being assembled. So we can send up parts and assemble them. Now, another part of that mission is going to manufacture a composite beam. And so that's sort of why I included it here, a 10-meter composite beam. And I'll talk about the application for that. But so that's an in-space demonstration mission to actually manufacture a 10-meter composite beam. So that's the first of a kind, really exciting for us. I think the launch of that mission is around the 2024. I'll go to the lower left, and it's another in-space demonstration mission. It's our OSAM, OSAM-2 mission. I'll mention the one on the upper left was the Maxar companies producing that for us. And the one on the lower left is the Made in Space company. Give those guys some credit for what they're doing. So on the lower left, you see those 2 solar arrays. This mission is all about deployment of those composite beams, again, about 10 meter. And we're either going to do 1 or 2 of the deployments of those solar arrays. And the idea is we're also, in space manufacturing, we're trying to build big infrastructure, maybe in space. Power is the limiting factor. And so we need to get more and more power. That's more and more larger and larger solar arrays. And so this demonstration on the lower left of OSAM-2 is a 10-meter solar array with a 3D printed composite beam. What we're really hoping for in the future is the capability to build 100-meter solar arrays, which we can't launch today.
Interesting. John, I have a few questions.
Yeah, go ahead.
Sorry to interrupt, but we got some folks who are really interested in your presentation. One from Dr. Kelly Matthews. How do you control thermal stability of a structure to within 32 nanometers with such a temperature range? And then Is it down to the material properties or design architecture or other factors?
So there's active ways to do that where we provide some shade, for example. But in the case of that composite design for JWST, it's in the design of the materials that really allows us to control to that level of thermal expansion. So that's really design and material selection that allows us to do that for that one. But that's a real problem. That's a real problem in space because especially if you go from nighttime to daytime, for example, and you want to operate, when it's cold and when you want to operate when it's heated. That's a real. So I'm really close to this OSAM2, and we're working through those thermal issues with that composite material now.
Excellent. I think, what's very exciting is with AI and machine language on material development, imagine what the future is going to hold, with all these technologies and with the data out there. The initial, when we put that video on, my mind was going crazy. How much data is involved? And imagine the capture of it and the analytics. So guess what? Maybe a year from now, maybe 2 years from now, or even tomorrow, with the new technologies coming in, it's going to become really something with material development.
Yeah, I really think so. I've got a chart later in the package, but I think that's one of the new greatest technologies that's going to give us some of the biggest benefits to being able to make our structures faster, more affordable, etc.
Right.
And have more performance. So I'll just finish up on this chart. I don't know how much time we have, but
you have time. Don't worry.
Okay. What we're really trying to do at NASA is to enable sustainable exploration and not have today we have to resupply like our International Space Station. It's close enough. It's only 200 miles away that we can resupply. But the further and further you get from Earth, whether you're on the lunar surface and especially on the Martian surface, if you've seen The Martian, which it's a movie I've probably seen 10 times now. There's no UPS. There's nobody coming with, there's nobody coming with supplies. And so you got to have a sustainable design paradigm to be able to do that. So that's what we're after. Next, I'll go to the next chart.
Excellent. A few more questions before we go on. One note of clarification, since we have so many folks from around the world. John mentioned DARPA. John, would you like to just spell that out for folks from around the world, DARPA?
Sure. It's the Defense Advanced Research. I'm not even sure I know. Defense Advanced. Somebody will put it in the chat.
I think defense was the key word. You got it right.
Project.
Thank you. Yeah. And then a few more questions. So here's an acronym from our friend T.R. Dreyer, HICAMP, HICAMP. Is that a program that you mentioned? He's interested in seeing, can he participate in that? Is it too late?
Yeah, so there's not any way to get involved today. It's a program that I said is in formulation. And so what I mean by that, we're designing that program this year, and it's typical when we design a program like that we would go into execution next year. So look for, and next year, I mean the fiscal year, which starts on October 1st. So look for that later in the fall.
Great question. Thank you. We have a question from Ricardo Brown. What 3D printing process and material was used for the beam structure? I'm not sure if that was your team, John, but if you do know, what 3D printing process and material was used for the beam structure?
Yeah, so I'm not exactly sure. I'm going to guess that it's fused deposition, FDM, fused deposition modeling, but I think you can find that probably on the internet.
Okay, Google can help us. Our friend Dr. Scott Beckwith, thank you, Scott. Does NASA maintain a material and processing database on all these unique materials for areas like space and Mars?
So we do to an extent. So NASA maintains a database for human spaceflight rated materials. because they have very rigorous requirements. And that's actually housed at the Marshall Space Flight Center. So it gets a little less complete when we're talking about missions that are not human rated. And so we might have some of those, but not all of those. One of the other things we do is we rely on others that have that kind of data, such as NIAR.
NIAR. And John, actually, you really mentioned something that piqued my interest. This might be a project for SAMPE, NIAR, and Marshall to get together on, a materials database type project. So the whole idea, you mentioned this before, the consortia of industry, partnership, government, and academia. Maybe SAMPE could help on that. So stay tuned for that, folks. I'm not going to make any promises, but that sounds like an excellent idea. I'll go to the next slide.
Okay, go ahead, and I'll just follow up. It's an area that's been identified as really important to what you mentioned earlier, AI and machine learning, because you have to have data to support those kinds of approaches. And like I just mentioned, our data is not complete at this point. So I'll breeze through this. I know I'm running out of time. I'm going to breeze through this really quickly.
We're actually at 13 minutes to go, so please don't rush.
Okay.
Thank you.
So I've said it's an exciting year at NASA. So if you look at the image on the left, that's an artist rendition, but that's our space launch system. And you can find on the web, again, we're testing the first stage of that now at our Stennis Space Center. And that's a huge rocket. And we're doing what we call green run testing. So we're testing the actual flight rocket to make sure it works properly. Then we'll send it to Kennedy Space Center for launch. And the current schedule shows that we're going to launch that in late fall of this year. So it's a big year. Now, the image just to the right of that, in the center of the page, the upper center of the page, is our astronauts climbing out of a Tesla vehicle, headed for the launch pad for the first SpaceX crewed mission to the International Space Station. There's this whole nuance between commercial and what we've traditionally done at NASA, and I think it's really advancing the technology much faster because of that. It's a little bit of a, I've said it's the Ford versus Ferrari competition a little bit. So I'll just point out we're the fiber placement machine that's at the center on the lower portion of that's at the Marshall Space Flight Center, and we have that so that we can do in-house. Of course, we do that with partners as well, so that we can do in-house research to supply these programs with advanced composites technology. So I'll go to
for our friends around the world who may want to visit Huntsville, Alabama one day, is there an opportunity when we get back to in person? Is there an opportunity for folks to visit, or do you need to be U.S. citizen or anything like that?
So you don't have to be a U.S. citizen. It's a little harder. We have to go through a little more process to get non-U.S. citizens in, but we usually host groups. But I bet we have 100 groups come through for tours and visits per year. So we have a lot of visitors come through.
Excellent. We'll have to do a SAMPE event there one day. That's good.
Next chart.
Thank you.
So I'm going to go quickly, but I did want to, I would be remiss if I didn't talk about our STEM program. We have a really great STEM program at NASA. I've listed on this chart some of the actual projects that you can apply to for STEM grants. And I won't go through each of those. You're going to get the charts, and so you can read what they are. Right. I just want you to know that within these projects, I took a look right before we started today, and we have more than 25 composites related projects within these projects. Over the last 10 years, we've had 1,500 composites projects. Wow. At NASA, and currently overall we have about 80 composite research projects at NASA. If you look at the project that at the bottom of this, it's called Space Technology Research Institutes. That's the biggest grant project that we award. every year. And one of those, so we don't do many of those. They're 5 years, $3 million a year. So we don't do many of those. But one of them and we just started them a few years back. One of those is a composites project. It's university led, and that one, in fact, is led by the University of, well, it's led by Michigan Tech. So that's a great project. I'll go to the next chart.
Sure. And then I think, as John mentioned, folks, you can get information of each of these programs on Google. So if you're looking for opportunities, collaboration, this is it.
So I put a lot on this chart, not really knowing that I was going to be limited on time. One of the things that I did want to talk about a little bit is how our product development, testing, and certification today, it costs too much. It takes too long. If we try to qualify a new composite material for a major human spaceflight program, that's one of the barriers. And certification is another one of those barriers. So I titled this a little less conversation, a lot more action. I think we need a lot more action in this area. We're still trying to get over the valley of death from the research that we do in this area to the actual application. And I think one of the ways to do that is with the computational modeling approach. You can listen to Dr. Byron Pipes about that. He's much more of an expert than I am. However, digital twin has become one of my passion areas. And so you see this little graphic on the lower right-hand side. That's a graphic that I built myself to talk about the aspects of digital twin computational modeling for discipline areas like composites, so that we can replace the physical resources, the exhaustive testing that we're doing today with computational approaches. Now, if you want to start a debate at NASA, just bring that up, the experimentalist versus the computationalist. And I'm not advocating that it's a complete substitution for the computational approaches, but there's got to be a balance. And I think we can do better and more by coupling the computational approaches with the experimental. And we're doing that to some degree. We're probably doing it best in academia today, and we need to bridge that gap between what we're doing in academia into application and practice, and we need to do it faster than what I'm seeing us do today.
I think your message is loud and clear. We need step change, and the digital twin seems like that could be an option. Previously, before I joined SAMPE, we were doing some work with Dr. Michael Greaves out of FIT, Florida Institute of Technology. And I think John knows Dr. Greaves, but Dr. Greaves coined the term digital twins. So, folks on the line, you're over 100 of you, you're still with us. That's a little bit of a bonus for you. Look them up, find them on the web. But I think John is onto something. I think this modeling piece and combination with what we have now is the solution.
So Dr. Greaves and I wrote the paper where I co-authored the paper where we coined the term digital twin. So you're correct. So he's a great colleague. He's a great colleague of mine, and that's why I have such a passion in this area, and that's why I have a ready-made graphic for this talk.
We didn't even plan that, John. I mean, come on, how great is that?
We did that in about 2010.
Excellent. So I know.
Okay, we better go to the next chart.
Sure.
I'll start ramping down. So I've said, hey, get out and get involved in your local tech and innovation hub. The new administration, President Biden, has something called a Build Back Better plan. And one of the elements or the highlights of that plan is around innovation hubs. And so from my position at NASA, from my position at the National Science and Technology Council, we're really trying to promote innovation hubs. Not that we haven't been for some time. I was part of the original Manufacturing USA National Network for Manufacturing Innovation. And so you see IACME that came out of that on the upper left-hand side. And again, guys, I got to apologize if I don't have your logo or your organization here. These are just some that I'm involved in, that were readily available to me, that I could get permission to use their logos, by the way. And the one on the lower center is from Dr. Byron Pipes at Purdue, the new Composites Manufacturing and Simulation Center. They just broke ground and had a groundbreaking last year. So I'm really excited to get up there and see him when we can get back together. I wanted to mention the one on the upper right. That's a colloquium workshop that we plan to hold in Auburn, Alabama, at their Center for Polymers and Composites. That's headed by their director, Dr. Maria Awad. And I saw Maria was on earlier. Thank you, Maria, for letting me show that today. And NASA is going to co-host that workshop. And we've tried to talk Raj into speaking at that workshop. We're really looking forward to that. But so that's a relatively newer innovation hub. And so I think that my message is get out and get involved. We did a study on the Manufacturing USA, and for each institute that's in Manufacturing USA, we saw more than 1,200 connections, close connections from those institutes to member organizations. And so that's a multiplier effect for you and for your organization to get involved in these tech hubs. And I put SAMPE right in the middle of that.
Right.
SAMPE may not be a tech hub per se, but the same benefits that you get from these connections in these tech hubs, you can get from SAMPE membership. So I wanted to make that point clearly.
Thank you so much. John, you know what? You've created so much interest in the topic. We're on to another question real quick, if we can. Where does NASA stand in the research or development of failure theories, standards for composites?
So that's an area of really importance to us. If you looked at my digital twin chart, you would have seen some of those one of those phases, and it's sort of design and analysis. It's in that phase between design and analysis, and so that's something that many of our researchers, maybe NASA Langley, maybe NASA Glenn, are doing critical work. The problem, while we're on the digital twin, one of the problems that we see is that kind of research, that kind of analysis is not closely coupled to the other phases of the life cycle. And so I think it's these computational approaches and the data that you talked about earlier that can help us couple. And it's all those things together that can shorten the life cycle and make it more affordable for us.
It's really a great time to be an engineer, scientist, because I think the future is so promising. Whether you folks, get involved with SAMPE, or John didn't put it up here, America Makes. If anyone's interested in 3D printing, as John mentioned, he was one of the original authors. We're about out of time. I do want to thank John for this. John, did you have any more slides or anything?
So I have 2 more slides. If you'll just click through them.
I will.
I don't really have to speak to them. I think I'll give 1 sentence each. I think there's a real connection between what we do in exploration, the discovery and science, and commerce. Oh, I just got to mention this picture on the lower right-hand side, because if you look at that, that's Walt Disney, that's Von Braun, and there was always this close connection between those two. The fellow on the most immediate left of that picture, Bob Swinghammer, is the guy that hired me at NASA. Wow. And I bring that up because he was a lifetime SAMPE member.
Oh my gosh.
Way back when. So
wonderful.
I have one more chart, and I'll leave it for you guys to read, since you're going to be able to download these charts from SAMPE. I tried to get a few of my friends that I think are some of the greatest within composites over the years: Byron Pipes, Les Cohen, Mick Maher, Mark Stewart, even one of my project managers from NASA, Chris Crumley. I threw something in there for myself, and I said, go do big things. That's at the top of my whiteboard at work if I ever get back to work. And why do I do it? I do it for the love of the game. It's been a great career, and I love what I do.
And
thank you guys for allowing me to speak to you today.
That is so wonderful, John. This has been an outstanding presentation. We're going to ask folks on the chat. You still have about 100 folks left. Tell us in the chat, yes or no, if you enjoyed this. Yes or no, simple as that in the Q&A. We are going to have a very quick follow-up survey that's going to come right to you again, a few minutes, just so we know that we're doing the right thing. John has, he spent hours on the presentation. It might have taken an hour of your time today, but we're very grateful. We're going to engage him. Thanks to Dr. Tate on more and more projects. But this is a very exciting time. And, the only way, as he says it, get involved, get in the game. So thank you so much, folks. In the Q&A, if you can, yes or no, if you learned something new, if you enjoyed it, and be sure to take the survey after. John, any closing comment?
Thank you guys so much for allowing me to do it.
Thank you.
Everybody have a great weekend.
Thank you, everyone. You'll watch out for the link. You'll get the link soon. Thank you. Goodbye. Goodbye.